Hello and welcome everybody, this is Noah, and in this video we're going to look at how the domain changes when we multiply rational functions. So for the examples that we're going to look at today, we're told to simplify the following products of rational expressions, noting any domain changes that occur during any step. And we're going to state the difference in the domain between the original expression and the final answer that we have after simplifying. Get myself a little room in here. So this is really an extension of what we did in the last set of videos. I'm going to look at factoring the top and bottom in any way that we can. So the 5x plus 7 doesn't cancel, or doesn't factor rather. We can see that it does cancel, and I'll do that in a moment. But before I do, I just want to note that I can factor out with that 54 minus 12x. I could factor out, let's see, 6 goes into both of them. We'll be left with 6 times 9 minus 2x over 5x plus 7. That's nice. I'm going to go ahead and cancel the 5x plus 7s now. Now, factoring does not change the domain in any way, but canceling does. Okay, so if I look right here at this stage at the beginning, the domain is the set of x such that x cannot equal 9 halves or negative 7 fifths. Let me show you where I'm getting those numbers from these two denominators, right? So 2x minus 9 cannot equal 0. So I add 9 to get 2x cannot equal 9. Divide by 2, so x cannot equal 9 halves. Or I could take that 5x plus 7 and note that that cannot equal 0 either. So 5x cannot equal negative 7. Divide by the 5 to get x cannot equal negative 7 fifths. So the domain at the beginning is that x cannot equal 9 halves or negative 7 fifths. Now let's cancel the 5x plus 7, top and bottom. So we'll have 6 times 9 minus 2x over 2x minus 9. And now the new domain is x cannot equal 9 halves, but now x can equal negative 7 fifths, right? Because we got rid of that part of the denominator. So the change is at x equals negative 7 fifths. So that brings to bear the question, are these two things really equal? What does it mean to be equal? If I'm saying that this line here is equal to this next expression, two expressions or functions are equal only if they output the same value for every x value. So if x equals negative 7 fifths here, it's undefined. If x equals negative 7 fifths in this next location, it is defined. So that means that these are not truly equal. The difference is at negative 7/5. Okay, so what I like to say is these are equal unless x is negative 7/5. Other than that, they are totally equal. Okay. So the difference in the domain is at negative 7/5. In the original expression, it cannot be negative 7/5. In this new expression, it can. Now, we can actually reduce this more. What I'm going to do is I'm going to factor a negative out of the top. So this is negative 9 plus 2x over 2x minus 9. I'm going to do this slowly here. So this is negative 6 over, if I switch the order, this is 2x minus 9 here, over 2x minus 9. So I've got to factor that negative out first. But now I can cancel these. And when I do, I get negative 6. And here, x can equal 9/2, right? We've gotten rid of that denominator that kept us from it before. So these are equal unless x is 9/2. So I'm going to now talk about the difference between the original expression and this final expression. So I'm going to bring them together. We have 5x plus 7 over 2x minus 9 times 54 minus 12x over 5x plus 7. And we can say that this equals negative 6 unless x is negative 7/5 or 9/2, right? If x is one of those two numbers, they are not equal. The domain here is the set of x such that x cannot equal negative 7/5 or 9/2. And the domain here is everything. We can plug any number in there, negative infinity to infinity. So the domain changed in that manner. So if we want to say that the original expression equals negative 6, we have to note that that's true unless x is negative 7/5 or 9/2, in which case they are no longer the same thing. All right, so I want to do these a little bit quicker. I'm going to do a little less explanation as we move into the more examples here. I'm going to move over to part B, where we have 6x squared minus 14x minus 12 over 6x plus 4 times 2x plus 4 over 2x squared minus 2x minus 12. And I want to begin by factoring as much as I can, top and bottom. I'm going to factor a 2 out of the top to get 3x squared minus 7x minus 6 over 2 times 3x plus 2 times, on top I have 2 times x plus 2 over, factor out a 2 times x squared minus x minus 6. Now when I cancel the 2's, that doesn't do a domain change. Don't have to worry about that. I do need to keep factoring though. The top, the 3x squared minus 7x minus 6, this we can factor as 3x, and then an x in the second one, and then I need, I think if we do 3 here and a 2 here, I need a minus 3, that'll give me a negative 9x, and then a plus 2x would give me a minus 7x in the middle, over 3x plus 2, times x plus 2 over, and x squared minus x minus 6 can factor as x minus 3 times x plus 2. And so it looks like a lot of things cancel. In fact, it looks like everything cancels, huh? 3x plus 2's cancel. The x minus 3's cancel. And the x plus 2's cancel. If everything cancels, that means this equals 1. So let's note the domain before that. The domain, for the first three, the domain is the set of x such that x cannot equal negative 2/3, 3, or negative 2. And that comes from 3x plus 2 cannot equal 0, x minus 3 cannot equal 0, and x plus 2 cannot equal 0. And so we'd subtract 2 and divide by 3. X cannot equal negative 2/3, x cannot equal 3, and x cannot equal negative 2. Now when we cancel them, and I just look at 1, the domain here is all real numbers. Like there's 1's just 1. There's like if x is 5, then the output is 1. If x is 7, the output is 1. Like if I were to graph the original, and I would graph this would just be a horizontal line. Here's my x-axis, my y-axis. This is just the output is 1. The original expression would look exactly the same, but at negative 2/3, at positive 3, and at negative 2, it would be undefined, so there would be these holes. So the original would have these holes, but the new one with just the 1 is just that horizontal line at y equals 1, and that has a domain of all real numbers. So what I'll say now is that these are equal unless x is negative 2/3, 3, or negative 2. And in fact, I want to link that not just to the previous line, but to the original line, right? We're comparing the original expression to the final expression. This seems like, why are we talking about this? It's actually it's important to note when things are different, right? As we're investigating something and saying, are we really simplifying these so that these are equal? The answer's like, kinda, pretty much, except for these couple of key places where they are different. So we want to just be aware of that. And if you go on to Math 111, you're going to be graphing these by hand, and it's going to be really important to note those differences there and understand when you get a hole in the graph. And so it's going to be important for that aspect as well. Let's do a couple more here. So part C, we have 2t squared minus t minus 6 over 2t squared minus 3t minus 2 times 2t squared minus 5t minus 3 over 2t squared plus 11t plus 12. We want to begin by factoring as much as possible. The top left, we've got 2t squared minus t minus 6. And so I believe we can factor this 2t something, and then we need a t in the second set of parentheses. And I think a 3 and a 2. If this is a 2 and this is a 3, we'll get 4t. And then a 3t, if we do minus 4t and plus 3t, that'll give us the minus t in the middle. In the denominator, we can factor this. We need a 2t and then a t again. And we want a minus 3 in the middle. So if I did like a minus 2, that'll give me negative 4, and then a plus 1 here, that will give me minus 3, and those multiply to be negative 2 like we want. It's good. And we can see the t minus 2's will cancel. And then top right, we have 2t squared minus 5t minus 3. Should hopefully be able to factor this. 2t, and then need something there, and then a t. Use some space. So we need a 3 and a 1 to make the minus 3. Try a 3 there and a 1 there. That'll give me a minus 6. If I make that a negative 3, and then a plus 1t would give us the minus 5 in the middle. In the bottom, 2t, and then t again. second set of parentheses, and we need it to multiply to be 12. We'll try 4 and 3 to start, have 8 and 3. That's 11 if these are both positive. There we go. Cool. So now I can note the domain for these first two lines. This is the set of t values such that t cannot equal -1/2, 2, -3/2, or -4. Right? From there, that's a -3/2 wouldn't work if we subtract the, I'll write them out. 2t plus 1 cannot equal 0, so t cannot equal -1/2. T minus 2 cannot equal 0, so t cannot equal 2. No, I want to put all these on the other side. I'm just encroaching upon part D there. That looks better. We also had 2t plus 3 cannot equal 0, so t cannot equal -3/2. And then we had t minus 4, or t plus 4 cannot equal 0, so t cannot equal -4. And I don't want to indicate, it looks like that domain equals that. Okay. There we go. Now we'll cancel and see how the domain changes. So we can cancel the t minus 2, and we can cancel a 2t plus 3. We can cancel a 2t plus 1. So we'll say that this equals t minus 3 over t plus 4. Here the domain is the set of t such that t cannot equal -4, and that's the only restriction now. So you can say that these are equal except when t equals the other things, -1/2, 2, or -3/2. That's where they're different. Those two things, the original and this new simplified version, are different when t is -1/2, 2, or -3/2. All right, let's do one more. We have 2t squared minus t minus 21 over 3t squared plus 5t minus 12 times 4 minus 3t divided by 2t squared minus 5t minus 7. We'll begin by factoring. 2t squared minus t minus 21. I need a 2t and then a t. And I think like 7 and 3 maybe. 3 and 7, that would give us a 6 and a 7. We want a -7 and a +3. So that I have a +6 and a -7 add up to a -1 in the middle. Over on the bottom, we'll need a 3t and then another t over here. And we want 12, so a 4 and 3 maybe. 4 and 3. So that'll give me a 12 and 3. That doesn't add to 5. Let's maybe switch them. 4 and 3. It's a 9 and a 4. That'll work. If I do a +9 and a -4, that would be a +5. Go times 4 minus 3t, that doesn't factor at all, over 2t, leave some space, open a new one, t, leave some space. All right, I need a 7 and a 1. If I did a 7 over there, I'd have a 14, and a 1 couldn't make a 5, so I'll try the other way. 7 and 1. This will be a 2t and a 7t, so minus 7 and a plus 2t would give us a minus 5. We'll cancel what we can, but let's actually note the domain first. So the domain is, let's see here, we've got 3t minus 4 cannot equal 0. So t cannot equal, add 4, divide by 3, 4/3. We have t plus 3 cannot equal 0, so t cannot equal -3. 2t minus 7 cannot equal 0, so t cannot equal 7/2. And then t plus 1 cannot equal 0, so t cannot equal -1. So the domain is the set of t values such that t cannot equal 4/3, -3, 7/2, or -1. Now we'll go ahead and cancel what we can. The t plus 3's cancel. The 2t minus 7's cancel. So we'll have 4 minus 3t over 3t minus 4 times t plus 1. And these are equal unless t equals -3 or positive 7/2, right? Those are the two domain restrictions that we just got rid of by canceling. Now we can actually simplify this a little bit more. The 4 minus 3t and the 3t minus 4, those are the same thing but opposite each other, the opposite signs. If I put a -1 on top and then switch that to 3t minus 4, see how that -1 would distribute across and give us a positive 4 and a minus 3t? So these are still equal when I pull out that negative and switch the direction. So I can cancel the 3t minus 4 and get that this equals -1 over t plus 1. And then these are equal unless t equals 4/3, because that was the domain restriction that we just removed by canceling there. And so finally I can say that the original is equal to -1 over t plus 1, except at t equals -3, 7/2, or 4/3, where the original one would be undefined while the final one is defined. Go ahead and work on the next try problems. In the next video, we will go ahead and walk through the solutions to those. Thanks for watching. I'll see you soon.